session. And I thank Kalpana ma'am and all the organizers for giving me the opportunity to have a discussion about the topic of today's discussion. We'll go into a while. So, just to make clear, am I audible? Clear?
Yes, sir, you're audible.
Thank you. So, let me share my screen. Uh, is my screen visible to all?
Yes, sir, it's
Oh,
visible.
right. We'll go. So thanks everyone for joining. So myself, Ben Samuel from AD Instruments, and the title for today is Getting Data Right. So the core concepts in biosignal data acquisition. So just a brief introduction about our company. He's our founder, Mr. Michael McKnight. So we have been in the business for over 35 years now, and our success formula is make the best products we can and make them as user friendly as possible and show our customers why the products are the best and the value what they bring, and about the support, the customer support that we provide after the sale. So we are the only company in India, I mean, that is related to data acquisition or the signal acquisition that have a direct presence or the direct company presence in India. So that is mainly for the support. So when we say support, it is not only related to like surveys or technical aspects. We mainly cater into the application oriented. Say, for example, like if a customer is working on animal surgeries or animal related research. So we people are trained directly by the company in Australia. So we are headquartered in New Zealand and our manufacturing things are in Australia. So we are directly trained by those people to handle the application oriented support. So the agenda for today's discussion would be the basics of data acquisition, so, and then how the AD instruments products are used in teaching and research, where I'll be covering what are the products we have and the specialized instruments that we have that we cater into both teaching, research, and into wider applications area, and then followed by a live demonstration of how the topics that I discussed are relevant and in live action. So coming to the data acquisition system evolution. So on the image, what you see here is something called a chymograph. It was basically invented in 1890s. So basically you can see a small smoke drum. So here, let me take a point. So this is something called a smoke drum. And there will be a paper like sticking to it, and then it has a lever. Once the lever moves up and down, basically it draws a graph. So that is how the data acquisition system evolved. If some of you people can visit a medical college in physiology department, you can still find these systems lying there because those people, I think, maybe in the last 20 years, like they were still using these chymographs. And then later in the uh, subsequent years, like in the 1960s, there is something called a polygraph. So this used a chart paper to record the data. So polygraph you might have heard in the forensic studies or the forensic people who say like there's someone who has committed a crime. If we are not able to judge him, then we put him to a polygraph test to identify his physiological responses. So basically, the data acquisition system is nothing but a polygraph. So there will be multiple signals put, and then we record the responses based on the questions or like other applications. And then this is the digital data acquisition system that came in 1990s. So I was talking about our founder. How this came into action is my founder's father, Dr. Tony, he's a physiologist. He had a project and he wanted his son's help to design a system to acquire the data. So he made this system to acquire the data, and it was actually a project which ultimately in 2013 it came as a Power Lab, which we are using currently as a hardcore data acquisition platform. This is the evolution of data acquisition. Next, we'll be going into the data acquisition basics. So you may all know how a data acquisition is happening. So basically, any mechanical signal. So it is acquired. We'll say physiological signal or a biological signal for this discussion. Any biological signal is acquired using a transducer. You can see in the image. It will be in the form of analog signal. Then in this analog signal enters the hardware, and then the signal processing happens. The signal is amplified, filtered, sampled, and the digital signal is fed to the computer in a form of digital display. The hardware we use is called PowerLab. So that is our mother product. And the software we use for display is called LabChart. So we'll be going into the details of this while during the discussion about the products. But when I say hardware, it is basically a PowerLab, and the software is called LabChart. So let's jump into the agenda of the discussion. So there are three things that we require to acquire a good data. First is select a suitable sampling rate, apply the correct input range, followed by choose suitable filter settings. So these three are very, very, very essential in acquiring a good data, a good biological data. So we'll go into the first part. So sampling. So everyone should be aware of what is sampling. So according to the definition, sampling is the process of converting a continuous analog signal into a series of discrete signal values by taking measurement at regular intervals. So the rate at which these samples are taken is known as the sampling rate or sampling frequency. You can see in the small image or the video representation here. So the blue line is actually the analog signal that comes, and how is digital samples are done is so the discrete points are taken at regular intervals of time, and that is basically known as sampling. So then there are some key aspects to sampling, how to select a proper sampling rate. So basically a fundamental step is converting this analog signal into a digital signal where the computer can understand what the signal is basically. So it will not be able to understand the analog signal. So basically, for the computer or the digital display to understand what the signal is, it should be made into a digital signal. Then discretization. So this continuous signal is broken into discrete points. So basically, you can see in the image here how the signal is broken into points. Then sampling rate. So as I told, the this is the number of samples taken per second. It is usually measured in hertz, or we can say it as samples per second, the number of samples per second. Then the very important thing we have to consider is something called Nyquist theory. So here, the important thing that we need to consider is to choose a proper sampling rate. What we choose a proper sampling rate, or what we choose a sampling rate less or more. So ideally, what the sampling rate should be is to avoid losing information and to accurately reconstruct a signal, the sampling rate should be at least twice the range of the highest frequency of the signal. So you will know the highest frequency of your signal. So you should keep at least double. So say for example, the frequency of your signal is 50 hertz. The signal should be the sampling rate should be at least 100. We normally suggest the customers to use more, like at least 5 times or 10 times, but the thumb rule is at least the sampling rate should be twice the rate of the highest expected frequency of your incoming waveform. What happens if the sampling rate is too less? What will happen is there will be loss of data, or we can say aliasing. Aliasing is something, a term we used normally. So if the sampled signal, or if the data is sampled as a less interval, then the data will be misinterpreted. So you can see, like, if you have seen movies, the car will be moving forward, but you can see the wheel is rotating backward. That is something, a basic example of aliasing. So that will happen when the sampling is too less. What will happen if the sampling rate is too high? There is nothing going to happen. Only thing is, it is going to take large part of the storage. So when we say a large part, usually the recording will be in like few MBs. So I've given a small formula here, like how the data will be calculated. So amount of data in bytes. So you can convert into MB or some. So the formula is 2 into number of channels. So basically, if you are recording in a data acquisition, there will be multiple channels. It may be 1, 2, 4, 8. It depends on your data acquisition. So 2 into number of channels into your sampling rate into your recording length. So in seconds. Once you feed in this value, you will get end up with a figure. It is like 5,000, 6,000 bytes. So that is going to be approximately 5 or 6 MB of data. So here, the main thing you have to consider about is in sampling is the Nyquist theory, where the sampling rate should be at least twice, and it should not be less. It can be too high, no issue. There is no going to be loss of data. Only thing is there going to be a large amount of space that is going to be taken. Secondly, we'll come into the, so before going into the next aspect, I'll just show you a image. So here on the green graph, what you can see is a finger pulse. So basically it's a pulse recorded from the finger. So this is how a finger pulse normally. So each wave will have its own morphology. So you as a researcher will know the signals of your interest will have certain morphology. So this is how a normal finger pulse will look like. And you can see here it is sampled at 200 samples per second. Same on top, you can see it is the same finger pulse sampled at 10 samples per second. What happens is the entire morphology is changed. So rather than a smooth pulse waveform, it is like visualized as a triangular waveform. This is a effect of improper sampling. I'll show one more example. So this is a periodic waveform. You can see the red is actually a signal. This is a periodic waveform, and you can see the bottom x-axis is the time 0, 1, 2 in seconds. So you can see this data points here one, here one. So basically in 1 seconds, it is sampling 2 times. So the sampling is 2 samples per second. And if you are sampling such signal at 2 samples per second, the signal will be completely misunderstood. So it is completely misrepresented. And this is called aliasing. This is what I was talking about aliasing. So going into the next aspect, input range. So range, to accurately record a signal, it is important to set a proper range. So many systems like many systems use gain when looking at an amplified signal. So range, but is inversely proportional to gain, and is more useful concept than gain because it relates directly to the signal. So we will come to that. So you set the range greater than the signal amplitude. So you know the amplitude of your signal, so you set a range accordingly. So if you set a high range, you can still see the data, but the resolution will be very poor. But if you set a low range, there will be data loss. I'll just show an image here. So you can see here, the amplitude of the signal is 1.2 volt. This is the blue one is the actual signal, 1.2 volt. But you have set a range as 1 volt. What happens is the signal will be recorded till 1 volt, and the top, the 0.2 volt is chopped off or clipped off. So again, you are not able to see a clear data. But if you set a high range, what happens is you can see the data in this point, but it will be a low resolution. So it is better to know your amplitude. Say for example, if your signal is like 1 volt, you set a like range as 2 volt. So you can see a data with a better resolution. So I cover all this during the demonstrations with examples or the explanations what I have given here. Next is filtering. So filtering, why do we need filtering? So in a signal, there will be something called noise. So basically, there is nothing but an unwanted signal. So we have to filter those. For that, in our hardware, the power lab, we have something called hardware filters. And then in the software, we have something called software filters. Hardware filter, we have to be very sure of what we are doing in the hardware filter, because once the signal is acquired, you cannot revoke those settings. So whatever the signal is coming in, you have to be very sure. Like there are hardware filters, like say for example, there's a hardware filter called mains filter. That is, you already know it is just to eliminate the 50 hertz mains noise. So once it is set, is set. You cannot revoke the settings after signal data acquisition. So basically, when you are acquiring a raw data, you have to be very clear, very precise. You have a better understanding about the signal morphology and whatever filters you are going to set. The software filter is nothing but post acquisition. If you want to do any filters, you can still do that. So, for example, I'll talk about EEG, electroencephalogram, the signal acquired from the brain. So you have acquired a raw signal. Then there is something called alpha, beta, gamma, theta waves we have to extract. So what we can do is in the software, we can assign one or three or four channels. You put a software filter and put the bandwidth. So for EEG, we'll use a band pass filter and we'll put the waveform and it will extract the alpha waves and beta waves and the waves of your interest. So here I have a small explanation. So this is the original waveform. You can see here our original waveform. So basically this has both high frequency and low frequency components, as you can see. If I apply a low pass filter, all these high pass frequencies are blocked. You can see how the waveform is smooth, eliminating the high frequency components. If I apply a high pass filter, you can see the low pass bands are blocked. This is a small explanation about the filtering. So you can be choose multiple filters. There are filters like all the filters are available: low pass, high pass, notch, band pass. So all these filters are available based on the application and your interest. You can choose different filters. Then there are some additional points which I'll explain. So there are in the software there are other options you can do. Smoothing. So smoothing is nothing. It is another means to remove the high frequency noises or the clutter from the signal. So you can do all this in the software. There is something called units conversion. Say for example, you are uh, acquiring a signal in X units, say for example newtons, and you want to convert this to percentage, you can still do that. Then there are cyclic measurements. So if there are any cyclic waveforms coming in, you can use something called cyclic measurements to derive the rate, period, or some high, like the maximum, minimum. All those things can be done. I'll cover everything in this demonstration. And then arithmetic calculations. So basically any arithmetic formula, like if you have a custom formula, you can put a custom formula, or if you have recorded two signals and if you want to add those two signals, you can still do that. All those custom signals, like the trigonometric functions can be also incorporated. Then if you want to find the integral of a signal, so basically it's the area under the waveform. If you want to have the integral, you can do that. Or if you want to find the derivative, the first order or second order derivative, you can still do it in the software. One example of this derivative would be a ventricular pressure waveform. And if you want to find the change in pressure over time, so you can just use a first order derivative and uh, find the derivative of the waveform. In summary, about the basics, so you can see here, define the variables you need to be measured, convert the physiological effect to voltage, that is nothing but sampling, choose the proper sampling rate, set the proper range, apply the appropriate filter, and then these two are additional points. Like if at all your transducer needs a calibration, you can do a calibration and set up the channels. So there will be a lot of channels available. So few channels you can use it for acquiring the data, and rest of the channels you can use it for multiple calculations. I was talking about the arithmetic, the cyclic measurements. You can use it for various other calculations. So any questions so far? Okay. So if anything is there, we can like discuss towards the end of the demonstration also. Coming to the hardware, which we call Power Lab. So Power Lab is the heart of our system. So basically, it can be available in 2 channel, 4 channel, or it can go up to 32 channel. And we have different models. I think like if you are, say for example, if your study is like only for 10 channels, we can give or customize a system for any channel. So different models are available that is suitable for teaching, research, and for both. So the main USB software system is it has a very high sampling rate without any data loss. So the sampling rate of our system is we have an aggregate sampling rate of 4 lakh samples per second. This is the aggregate. So if you say if you are using a 4 channel system, this 4 lakh will be split. So each channel will be using 1 lakh samples per second. And it has a 16-bit resolution. So coming to resolution, what is the resolution? Basically, a 16-bit resolution refers to how precisely an analog signal can be represented when converted to a digital form. So here bits represent the number of binary levels used to encode the signal. So 16 bits means it is actually 2 to the power of 16, which comes to 65536 discrete digital steps. So these many steps it will take to interpret a signal. So what happens is it will break your input signal into 2 to the power of 16 slices. This By this, it detects very small changes, and even the smallest signal will be visualized with highest accuracy or better resolution. Then it gives a smooth and a detailed digital signal. That is about the resolution. Like at this point, I would like to ask if you see most of the data acquisition signals that we using in biomedical departments or biosignal acquisition will often use a 16-bit ADC. I mean, analog to digital converter. Do you have any idea why? It is because biomedical signals are very, very low in amplitude and noisy, and it will often require extraction of fine details. That's why we use a 16-bit ADC. So some of the examples I can give about the biological signals is the ECG. The amplitude of the ECG signal will be like zero point 0.5 to 5 millivolt. If you are coming to EEG, it will be even lesser, 10 to 100 microvolt. EMG, the electromyogram that is from the muscle activity, it is like around 5 millivolt. So why the resolution should be high is if you take a EEG and use a low resolution DAQ, say for example, if you use a 10-bit DAQ or 8-bit DAQ, what happens is you cannot even visualize the signal. That is how it works. So that is why in biological field we use a 16-bit data acquisition. So in summary, if I want to summarize about the resolution, it is because why I'm talking or emphasizing more about the resolution is it is very important. The resolution and the sampling rate of a data acquisition is very, very important, and that's why I'm emphasizing on these points. So the summary of this resolution would be the signals are very tiny, and the medical standards they demand high accuracy, and we need a low noise signal. So basically, for all these things to be covered, we use a high resolution DAQ. So our data acquisition system have a 4 lakh sampling rate and a 16-bit resolution. And then we, of course, we have the high pass, low pass filters, which we were talking about the software, digital and software filters. Then there are different technical points like the DAC will have digital inputs and outputs for like external instrument controlling or triggering, and all our instruments follows high international standards, including IEC standards. So these are some of the different models available, the 15T, 2060. Those are 4-channel DAC. So I'll be using a 4-channel DAC today for the demonstration towards the end of the session. And of course, we have a 2-channel, 4-channel, and a C series is something called, this is the C series, the image you can see. It is a modular DAC. Based on the number of channels or the customer's requirement, it can be completely customized. It can go up to a 32-channel DAC based on the interest. So this is a small visual representation of a 4-channel data acquisition. So on the top, what you can see is a 15T model, and bottom you can see is a 2060 model. So this inputs you can see input 1 and 2. These are general purpose inputs. So this can take any analog inputs in the range of plus minus 10 volt. So any analog signal that is within this range, we can acquire the data. So you can see here these are the input signals. Then towards the next, you have something called isolated stimulator. So this is basically a small isolated stimulator to give a small current. So there will be something study called nerve conduction studies where we'll be giving a small current to stimulate the nerve and record the activity. So it gives a current of up to 20 milliampere. This is a completely isolated simulator. Towards the end, you have a inbuilt bioamplifier. It is a two-channel universal bioamplifier. Bioamplifier in the sense it can record any biopotential. ECG, electrocardiogram, electroencephalogram, electroretinogram, electromyogram. So all these biosignals can be recorded using the bioamplifier. Then towards the end, you can see the output. So basically, it is basically a function generator. If you want to generate any signal waveforms, you can generate here. And on the bottom, the 2060 model, there is a trigger, so which that is not available on the entry level model. So it is basically to give a trigger, like if you want to trigger the power lab or any external systems, you can use the trigger. So the rear view is pretty simple, the communication and the power, whereas the 2060 has two additional ports. So this is the input and output, which we were covering in the previous slide. It is basically to control or trigger any external devices. So if you want to control Power Lab or if you want to control any external devices using Power Lab, you can still do that. And then there is a I2C connector. So basically, if you want to connect any external amplifiers, so you can connect here and it can be powered using the Power Lab itself using I2C bus. So this is about the hardware. Coming to the software, it is called LabChat. Basically, it is called LabChat Pro because there are some additional modules available in addition to the normal available features. That is why it is called LabChat Pro. So LabChat is a very user-friendly software. So our motto itself is to give a user-friendly software, hardware, and make science easier. That is our motto. So you can record up to 32 channels. So if your recording is only 4 channels, you can use the other channels for uh, different calculations. And then there are online calculations like arithmetic integral, which we have covered. You can generate a customized simulation. You can record from multiple devices. Both online and offline analysis can be done. Online and offline analysis here, what I mean is you can do the analysis while sampling. While recording the data, also you can do a sampling, I mean analysis that is online, and post analysis that is offline. Then there is a feature called data pad. That is within the software, you have something kind of an Excel inbuilt. So you can do all the calculations, you can extract the values directly there, and you can do macro operations. Say, for example, you are doing a study, let's say on 100 subjects, and the operating procedure, the standard operating procedure is the same. So what you can do is you can put a macro. So you don't have to do the steps each time. So once the transducer is connected, you can actually design the steps required for your research and turn on the macro. So all the clicks, all the data can be taken automatically. Then you can import and export the data in different formats, including MATLAB. You have a frequency and power spectrum analysis. Then there are different analysis models. So this comes into the pro modules. You can do analysis or acquisition and calculations. But if you want some automated analysis modules, then it should be like you have to purchase a pro. So there will be different modules including HRV, ECG, blood pressure, dose response, different modules. Then there is one interesting module called video capture. Here what happens is it can directly work with a USB camera or your laptop's camera, where the data and the video can be recorded, synchronized, and like you can post acquisition if something has happened to the subject, or if you take the cursor to the particular area on the video or the particular area on the data, you can see what has happened to the data, simultaneously what has happened to the subject. This usually will be done during some seizure studies or epilepsy studies or sleep related studies. Usually this video capture modules will be more used. In engineering, maybe during data analysis or during exercise, some biomechanics studies, this can be of much help. So in teaching, we have something called the LabChat software. So this is the software which we were discussing. It can be used both in teaching as well as research. Then we have a software called Lab Station, which is dedicated for teaching. So basically, it will have interactive lab sessions. So it will have modules or pre-labs or recorded data or how to use the system, how to connect the transducers, how to do the settings. All this will be available in lab station. That is primarily lab-based teaching oriented. And then it is we have something called LT. This is also an interactive learning platform, but this is cloud-based. The difference is it's offline teaching platform. LT is nothing but a cloud teaching platform, and we have different sensors. We call it USB sensors rather than a DAQ. We just plug in the sensors to the USB. Say for example, ECG means you just take the ECG sensor, connect to the USB, and you can acquire the data live. But it is not a research system because we cannot like export data and take it into multiple things. And then coming to different kits, so we have different kits available. So based on the study, you can choose multiple kits. So on here, what you can see is something called a human physiology kit, where it will have a blood pressure sensor, a pulse sensor, and a grip force, respiratory belt, or such things. So down what you can see here is a gas analyzer system for metabolic studies. And similarly, you can see on the right, you can see here it is a wireless heart rate sensor where you put the belt to the chest and you can record the heart rate wirelessly. So how to design a research system is you need a data acquisition primarily. So based on the number of channels, you will have a data acquisition and then signal conditioners. So certain signals like require additional signal conditioning. Say for example, if you are recording pressure, then you may need a bridge amplifier. Or if you are recording something like a ECG or a high gain signals like neural signals or uh, electrogastrogram, then you need a high gain bioamplifier. So they are nothing but signal conditioners. I'll just show in the next slide what are the signal conditioners we have. Then comes some specialized instruments. So if your study is something on specialized segments like wireless or NIBP, then the specialized instruments is required and the required transducers and accessories will make a complete research system. These are some of the signal conditioners available. A bioamplifier. So these are available in different channels like 1, 2, 4, 8. We call it single, dual, quad, octal for recording multiple signals like ECG, EMG, EOG, EEG, and ERG. There are multiple biosignals you can record. Then if you want to record pressure or any force, you have a bridge amplifier. It is also available in multiple channels. Then say for example pH, conductivity, you can use a pH amp. And there is something called galvanic skin response or electrodermal activity. It is basically the response to the skin conductance. So if you want to measure the skin conductance, you can use the GSR amplifier and then the spirometer and gas analyzer to record the respiratory parameters and stimulators. So if you want to do any external stimulation, we can use the stimulation. So all our systems can be used in both human and animal research. So our prime areas of research would be like physiology department, engineering department, and then pharma companies. All these people will be using our systems widely. So these are some of the additional signal conditioners for blood pressure, EOG. EOG is nothing but electrooculogram where we use to record the movement of the eyes, and then the oximeter to record the SpO2, and then there are a few other uh, signal conditions. So then coming into the research systems, there are the research systems are specialized systems, we can say. There are some systems for recording signals exclusively. First is a human NIBP system, exercise physiology system, blood flow, psychophysiology, ecovital, it's a wireless physiological system, and a pulse wave tonometer. So you can use this system along with your data acquisition system, I mean the Power Lab, and record data simultaneously. So all our systems works with only one software, that is laptop. It can be any combination. So for example, it is with Power Lab and human NIBP, it is possible. Power Lab and Ecoid, it's possible. Or in any combination, multiple compatible devices can be connected and you can design a research system accordingly. So it is possible to make a tailor-made configuration based on your research or your study requirement. So we'll be taking few more minutes, like maybe around in 5-10 minutes, we'll complete this presentation. This will mostly cover the specialist instrument, and then we'll go into the demonstration part. So I was talking about the human NMBP system. We know about the blood pressure. So it is something we use a cuff in the hospital, like it is called oscillometric technique. We put the cuff to the arm and you take a blood pressure. So you can see the doctor or the clinician will use a stethoscope to listen to the sounds and give a blood pressure. And there are digital systems also. What happens is the BP recording will take at least 30 seconds to 1 minute for you to get a blood pressure. The difference of this system is if your study involves continuous blood pressure recording, then this is a good system to go for. What happens is you can see here, this is from a company called FinaPress. We have channel partnered with FinaPress Medical Systems to make that system compatible with our software. So basically, let's say let's take a application of physiology department in a medical college. There is something called autonomic testing. So where the subject will be asked to lie in flat position or supine position, and then he'll be tilted. There will be something called tilt table, and then he'll be suddenly like tilted to 70 degrees in 0 to like 15 seconds. What we want is what is the change in BP during the 15 seconds? If there is a dip in diastolic blood pressure, or what exactly happened during the tilt. So there is something called syncope. It is nothing but sudden loss of consciousness. If the subject has syncope, then what was the blood pressure? We cannot find this blood pressure using the normal sphygmomanometer or the digital blood pressure monitors. For that, you need a continuous BP monitoring. The technique that is incorporated here is called volume clamp. So what happens is you can see on the image here, we use a finger cuff instead of a normal regular brachial cuff. So the cuff will have two sensors, a detector, a light source, and a detector. So what will happen is we put the cuff to the middle phalange, you can see here, and the cuff will inflate. It will try to find the diameter of the artery. Once it finds the diameter of the artery, it will clamp. And then, based on the pressure changes, it will give the blood pressure. So basically, it is called volume clamp method. What happens is, if you give blood pressure for every heartbeat, it is called beat to beat blood pressure. If your heart rate is 100 per minute, you will have 100 BP recordings. That is what is called non-invasive human NIBP system. So it is a very accurate blood pressure system, and it has something called height correction unit. You can see this image here. Why this height correction unit is used is usually blood pressure is recorded at the heart level, but we are recording blood pressure here at the finger level. So to correct the orthostatic height differences, we'll use this. We'll calibrate this sensor. We'll put this together, make a zero. One sensor will go to the finger cuff, you can see here, and the big part will go to the heart level. Maybe we'll put it to the pocket, or at the heart level, we'll do a velcro, and it will change it will nullify the height effects. So the parameters are it will record the systolic pressure, diastolic pressure, mean arterial pressure, heart rate, and then there will be derived parameters. So there is an extension called non-invasive cardiac output. Using that module, you can derive the stroke volume, cardiac output, or total peripheral resistance. And this is best suited in yoga, exercise, and sleep studies. And coming to the next, there is the exercise physiology system. This is mainly to study the metabolic parameters. So there is a very important parameter. Like out of the topic, I would like to tell you something. Like this VO2 max is a very important biomarker used to assess the health of us. So it is used to assess the metabolic uh, wellness. So it is a very accurate biomarker to indicate the health of a human being. So basically, how it is measured is you can see here. So it has a mask. So there are technical aspects to it which we are not covering today. So this is the gas analyzer. So this will get connected to the mask, and the subject will be doing some exercise. And the VO2 is nothing but the volume of oxygen consumed and the volume of carbon dioxide produced. So this will measure. You can see on the graph here, there are multiple graphs. So this will record the VO2 and the VO2 max, also the parameters. So how this usually done in practical application is your age. Say for example, your age is 30. What they'll do is, the researcher will do is, they have a small formula, 220 minus your age. So 220 minus 30, it will take to 190. That should be your maximum heart rate. So what they'll do is they'll ask you to do exercise either on a treadmill or a ergometer. Treadmill means they'll like gradually increase the speed and the inclination. If it is a ergometer, then it is a cycle kind of thing. You may all know. We used to do that in gyms. They'll increase the load or the resistance. And as the exercise progresses, your heart rate will also go up. So we have to do that study till your maximum heart rate, and there will be a resultant value called VO2 max. So I'm not sure. I think it should be ideally 45, the VO2 max for a healthy individual. Uh, we have to improve the metabolic health. So it is a very like we normally say like blood test, renal function, kidney function test. Similarly, this is an unspoken parameter that is a very good indicator of our health. And then there is a blood flow measurement system. Uh, this is nothing but it uses a small fiber optic probe to measure blood pressure from any area, like any surface areas. This is also used in humans and animals. Predominantly, this is used in animals for brain occlusion studies, where the blood flow from the brain is recorded. But yes, it is used in humans also to record the blood flow. We have seen people using it in dental research also to measure like the blood flow from the gingiva. So there are different probes, the surface probes, miniature probes for both for different applications. Then there is something for psychophysiology research. Psychophysiology is nothing but it is the relation between mind and the body. So what we'll do is we'll give some mental stress or some stimuli. So basically auditory, visual or mental stimulation, external stimulus we'll give. In turn, we'll record the physiological parameters like galvanic skin response, EEG, brain activity, the eye activity, all the signals will record. This is for psychophysiology research that can be extended to your any other research. Like it is completely like modular to design a system ideal for your research. And there is one more system called wireless physiological monitoring system. It is called equator. If your study is for on wireless signals, then this can be used. You can see on the image here, it is a wireless belt. It can be worn just on the bare body. It will have silver fluoride coated electrodes. So basically, that will record the ECG. Then it has a respiration belt included. So your respiratory activity will be recorded. Then it has a skin temperature and it has a 3-axis accelerometer sensor also. So if you're doing some yoga studies, biomechanics studies, if you want to see the postural change or the activity, XYZ, the both 3-axis acceleration studies can be recorded. Then additionally, you can record like SpO2 and galvanic skin response wirelessly, any one at a time. So this belt will have an auxiliary port. So if you want to record either galvanic skin response or SpO2, additionally you can still record. And now we have an option to uh, record the core temperature also. Basically, it is a small capsule kind of thing which we take it, and then we'll record the uh, core temperature, and the capsule can be discarded or it will actually excreted after a few hours. So this is the final product for today's discussion. It is something called a tonometer. It's called a non-invasive pulse tonometer. So if you are interested in recording any studies like pulse wave studies, you can use this. This is how the sensor looks like. You can see how it is applied. You can record pressure from any arteries. So it either if it's of radial artery, brachial artery, carotid artery, femoral artery, any arteries, you just place the sensor, it will give a nice waveform. So basically, it is used in like studies include for arterial stiffness or autonomic function. Also, there is something called vascular function studies, and those cases this will be used. So this is the last slide. So these are the different recordable human parameters, both wired and wireless, that are available with our systems. So towards the first part, it is the human parameters, and towards the right is the animal parameters that can be done wired and wirelessly. I didn't cover any animal products because it is not related to our portfolio. So I have made the presentation short to stick to what we really want. Thank you. Any questions? Or can we go into the demonstration?
Oh, what about synchronization of signals collected from different electrodes?
Every signals are time synchronizer. All the signals you recorded here, made
Okay.
if it's from data acquisition hardware or if it's from multiple signals, I mean multiple uh, specialized equipments, all this data are time synchronized. All these data are synchronized recorded, time synchronized. If you are recording video also, that is also time synchronized recording.
We don't need to do any specific step regarding synchronization.
Nothing, sir. Nothing.
Okay. Thank you. Thank you.
Excuse me for a minute. I'll just connect my hardware. So I'm not going to like show the hardware because it's just a power lab. I was showing in the presentation the rear and front side and the rear side. So I'm using the same power lab here. So for uh, a quick presentation, so I'm going to show you maybe 2 or 3 signals. So this is actually a finger pulse transducer we were talking about. So you can see here, this is a finger pulse transducer which I'll be wrapping around the finger. So this will give you a finger pulse recording. And then this is a hand dynamometer. So you can see here, it is basically a strain gauge. So once you apply the force, it will record the hand grip strength. And then I have the ECG connection. So basically, just a cable, just what we use in hospital. So basically, it is for ECG connection. So just give me a minute. I'll just connect the hardware. So I'll reshare my screen. Is my screen visible? Can anyone confirm?
Yes, sir.
Thanks. So this is how a lab chat software looks like. So I just connected the finger pulse transducer. This is just the home page. I just close this. By default, it takes like 8 channels. So if you go to the setup and channel settings, you can change this anytime. Like you can rename your channels here. Like uh, I'm using a pulse, and the second channel maybe I use a grip force. It is basically a hand grip sensor. and the third channel I'll use for ECG. Likewise, you can rename the number of channels. You can take up to 32 channels. If I put 32, you can actually take 32. See, what happens is I have a small laptop, so it is not able to fit to the resolution properly. So if you have a bigger monitor, then that will be best suited. Like I was talking about multiple channels to use it for different calculations. So this is how it works. Sir. Now I have not done anything. So basically I have opened up the software. I've just connected a finger pulse transducer to it. That's it. You can if you have the settings done straight away, you can hit the start, or we can see how the signal acquisition is done. We were talking about sampling rate. So here on top you can see sampling rate. So you can go as slow as these many, like 10 samples per minute. Very slow samples can be done, 1 samples per second, and 100,000 samples, basically 1 lakh samples. So I was telling about the aggregate sample rate, it is 4 lakh samples. So it's a 4 channel system where it is split to 100 sampling rate, 100,000 sampling rates per channel. So now I've connected a finger pulse transducer. You can recall uh, like the slide where I have put an image of a regular pulse and the pulse that is sampled at 10 seconds. So ensure. Now what I can do is, for your understanding, I'll just expand the first channel alone. And I'll set the sampling rate to 10. I'll hit start. So since the sampling rate is very less, you can see, for understanding, I'll expand the data. You might recall this is not actually a finger pulse. I was talking, this looks something like a triangular waveform. This is what happens when you undersample the data. Now I'll just stop. I'll put the samples to maybe like 200 samples per second, and you can see the difference. I'll just compress the data. Can you see the difference? It is a finger pulse. So if you do a proper sampling, you can get the proper data. If you do a more sampling, like 1,000 samples per second, it is not going to harm anything. Just that it is going to take more space. So I'll just again compress the data. So it is a finger pulse waveform. This is how it should be done. This is about the sampling. So I'll just equalize the channels. I'll go to the pulse. There is something as input amplifier. So here I'll just hit this and auto scale. We have to set a proper range. You can see the maximum amplitude of the channel is around 0.1 volt, but the range we have set is 10. This affects the resolution. So what we can do is, what I'll do is, now we can see, I'll put a less, so I'll put a 20 millivolt. You can see the signal is actually getting clipped. You can see nothing. I'll put 100 millivolt. I'll just auto scale. You can see that we saw it was a 0.1 m, but the top some areas are getting clipped off. So ideally, what you can do is you can put a higher, maybe a double 200 or a 500 millivolt, and if you see, the resolution will be very clear. And then there are some filters. So I was talking about hardware and software filters. So these are something but hardware filters. So once you do the settings and acquire the data, you can't change anything. So if you want to, if you can put a main filter that is just going to remove the 50 hertz main noise. And then if you want to put some, if you want to invert the signal, or if you want to apply a low pass filter, you can still do. Just hit OK and start recording. That is your finger pulse. These are the steps we used to follow. Since it's a cyclic pulse, I will show you. I was talking about cyclic measurements. So what I'll do is I'll use the fourth channel for cyclic measurements. I'll just go here. There's something as cyclic measurements. It's a cyclic waveform. So here what we have to do is you have to select your source. My source is channel 1 pulse. And these many parameters you can actually derive from a cyclic waveform. rate, period, frequency, count, mean, medium, standard deviation, all these things we can record. So for now, I'll measure rate. And there is something as preset. So this can be used in multiple applications. So our preset is a finger pulse from finger, cardiovascular finger pulse. Once you hit this and I start, you can see on the fourth channel, it gives you the rate. This is actually your heart rate actually. So if I do some nothing or something, it will change. This is actually your heart rate. So if you want to see any values, you can just click drag. You can see the values. If you want to see any values like this, you can do it for any calculation. Like all these things you can do, you can toggle around, you can open multiple windows, you can save it as a template actually. So this was one example on the basics of data acquisition. Then I'll move to the next signal. I'll just stop. I'll remove the finger pulse. I'll show you one signal. So I'll show you the hand grip. So I'll just go to the grip force. I'll do a zero. Certain sensors require a calibration. So I'll just put the grip force sensor that I showed you to a flat surface, do a zero. Now I'll just expand it. I'll expand the channel. I'll expand the values also. Now it is in flat position, it will be zero. Once you usually it is used to like assess the hand grip strength. So if I just press the sensor, you can see the values like 90, 100. So what I'm going to do now is I'm trying to give my maximum. I'm going to squeeze it hard as I can to see my maximum contraction. So you can see, I'll just stop for now. You can see, take the cursor here. It has gone up to somewhere around 500, 502 Newton. If your study involves not this value, and if you want to do a unit conversion, what we will do is, sir, we will select the maximum area and the minimum area. Just we'll select this area. We'll just, it's just a normal mouse operation. Just, or just click somewhere here, the maximum area and the minimum area. And then go to, there is something called unit conversion. It will show you the graph there. So what you do is, just select the maximum of some area, put it to your point one, mention as that is my 100. And this is the zero, we know. Put to the value, put as 0. Then change the units. So I'm interested in percentage to see the percentage change. Once you do that, just click OK. Uh, 1 second. So once that is done, it will be completely changed to percentage. Now this will be by 100 and this will be the 0. So now I'll start. So usually a test that will be done is once the subject does 100%, they'll be asked to maintain their 30% for 2 minutes. So they have to maintain the 30% for 2 minutes, where simultaneously the heart rate or the EMG will be recorded. Now it's easily visible that I'll just take it to 30%. We have to maintain at 30% for 2 minutes, or it depends on the application. Maintain it for 2 minutes and your study is done. So this calibration I just showed you in percentage. If you know the values, you can do this calculation in like a kilogram or any other parameters of your any other values of your interest. You can still do. So this is how the data signal is acquired, sir. Like I just stop. Maybe I'll reconnect the finger pulse transducer again. I'll just equalize the channels. So here we have seen pulse, hand grip. I have not shown you ECG. It is a similar signal. What you have seen, what I have connected the cables and the electrodes, but I have not actually connected on myself. So what you can see here is actually a complete noise. 4 channel we were using it for some what's that rate calculation. So if I want to say for example, like I'll take an example of arithmetic. I'll go to arithmetic. So our first and second signal doesn't make any sense for this, but just for your understanding how this thing works, I'll just show you. We are just going to go. I'm just choosing my channel one. There are different functions. You see, if you go to math, there are addition, subtraction, and then there are trigonometry, logarithmic. So there are different functions available. And use a mathematical function of addition. Just give. I'm going to add channel one and two. Just click OK. So basically, it is a summation of first and second channel. It's an arithmetic calculation. Similarly, you can do multiple other calculations. Now, I was talking something about data pad. This is something as an inbuilt Excel within the software. So if you want to see the data and this thing simultaneously, I just go to window and tile it. So you can see the both the things simultaneously. So there are different ways. So this is, I was talking about you can go with a number of columns, a number of rows, just like an Excel, but with much more like sense. Like if you see by default, it will actually take the mean of whatever recorded or the calculated channels. If I go to A, this column A, see these many things you can actually derive. You can set the Excel in such a way, these many things can be derived. Now statistics and it is the mean. If you go to the next column, if you want, if you don't want the statistics, if you want to put a comment or the slope, integral, information, all these things you can actually put them. So if I just drag some values and add to data pad, you are going to get the mean of the values. This is one way, offline analysis. What I'll do is, I'll just, there's something called time to data pad. This is while recording, you can actually see the data live. I'm going to do, I need every 1 second of data for every 1 second. So I've just done. Now it is configured. What I'll do is I'll just hit start. You can actually see the value automatically updated, the statistical value automatically updated live to the data pad. You can change the time to seconds or minutes or even smaller milliseconds. You can still do that. This is one way. There is one more interesting part. If you want to copy the data to Excel, you can just select and copy. But this software can be directly linked to your Excel. What I'll do is I'll just select all, put Control C, copy. For that, I think I'll just stop sharing because I have just enabled lab chart alone. I'll just open Excel and share my complete screen. Just a minute. So I've opened Excel. Now I'll share my complete screen. Yes, since I copied the data, I'll just go to Excel. Just right click. There's something called as paste special. Just click that. You paste as link. Just click OK. Once you give that, all the data that was available there is copied. Now what I'll do is just go to lab chart again. Start the data. So now you can see each second is being like analyzed here. And I'll go to Excel. You can see here that actually software is linked with the Excel. So each second of data is actually getting fed to the Excel. This reduces your time of exporting the data because whatever parameters you set or whatever values you wanted to extract will be directly linked to Excel and straight away during the recording it can be visualized live. So this is one interesting feature. Then there are different multiple modules. Like if I want to show you if you want to zoom a area, then you can zoom the window. Then there is something called a spectrum view. So I'll just close the data part and tile this window. So you can see here the frequency in which the pulse is coming. So I set the channel as 1. So you can change the FFT size, the window, there are different windows handling having all those things you can set. So you can see here the display, the FFT display and the spectrogram. This you can do it for any channels. Then I was telling we have specialized modules. So these are some automated modules. So ECG analysis, heart rate, metabolic, peak. If you have a peak, and then if you want to analyze that peak data, you can still do that. So finally, I'll just show you the ECG recording. I'll record live and show you how the module works, and we'll conclude the session followed by any questions. So I'll just connect the ECG electrodes. Just bear with me for a minute. So I've connected the electrodes. So for this, I'll just expand the third channel. So before recording, I'll just go to the bioamplifier and we'll see how the signal looks like. You can see we are getting the signal, but it is very small. You can just auto scale and see it is in the. You can see there are here. You can see there are noises. So we'll do the filtering. You can just see. So you can see the signal is in the range of 0.8 millivolt. So what we can do is maybe we put a 5 millivolt range. You can see this is better. And then I'll apply a 50 hertz low pass filter maybe. And I'll turn on the main filter. You can see the data is all the data is getting changed. Just click OK. Just start recording. You are recording the ECG. This is just a lead to single channel ECG. You can do it for multiple channels. If you want to do it for 2 channels, you can do, or if you want to do for a multiple channels, then you can go for quad or octal amplifiers. So I'll just show you how the analysis module works. So there is an automated analysis module here. So we have to follow few steps to go for the analysis. Follow step by step. Go for settings, first thing. Next is go for classification, and it is done. So initially I'll do settings. So we need to select our source. Our source is channel 3 ECG. So if you are doing some selection, then we have to give some selection, or if it's a whole channel analysis, it's a whole channel. And the preset. So we are doing it on humans. Simultaneously, it is going to be, it can be used on animals, small animal, large animal, etc. So I'll select the preset. Just click OK. Now you can see here, basically you know ECG waveform, right? There's something called DQRST. Here the R waves are getting picked up. That goes to beat classification. So it is nothing but based on the morphology of the waveform, we have to include the beats. So it is just to remove any ectopics. Whatever beats or whatever the small dots you see here are the beats. Whatever you take it to this box will be taken for analysis. Now that is done. These 2 steps are done. Your things will be ready. Now if you just go to averaging view, it gives you an average. If you go to the table view, it will actually give you all the values. For this, it is very difficult to see, I think. I'll just show you. It will give you these values. RR interval, PR interval, heart rate, QRS, QT, all these values will give you. And there are different plots. There's plot QT versus this thing plot. There's one interesting plot called as waterfall plot. This is basically a 3D plot. So this value doesn't make sense because we were recording noise for a last time. What I'll do is just go to the window. I'll tile the data. Now you can see everything simultaneously together. Just I'll go to ECG, clear the analysis. I have cleared everything. Now there's something as analyze while sampling. I'll enable this, thereby data like analyze the data during the recording. I'll just click here and start. Now you can see data will be plotted live. Your ECG graph is plotted live. Your table is getting automated live. This is how it works. This is actually a 3D waveform. You can just toggle around and see. So this or like there I can give you an example. In some animal studies, what they'll do is they'll induce the animal some stroke or heart attack, let's say. So they'll give some medication. So what happens is this actually each wave getting superimposed over the other. So once the drug is given or the heart attack is induced, you can see the morphology of the waveform getting changed or the interval of the waveforms getting elongated or prolongated. All these things you can just visualize in a better way. You can see how the drug is working. So it is just a good, nice representation of how this thing works. Yes, that's all I have from my side. And thank you. I'm open to some questions if you have.
Hello, sir.
Yes, sir.
Sir, are you dealing with identification of VOC components, sir?
Identification of
Volatile organic compounds like alkyl benzene in terms of biomarkers in finding lung cancer diseases.
no, sir.
Oh, okay, fine. Okay, sir. So since you are into this respiration concepts and all these things were involved in the presentation,
Mhm.
that I may thought of asking you that if you are into that, I need some sort of help from you, sir.
No problem, sir. Unfortunately, we are not into it, sir.
Okay, sir. Thank you.
So if there are any more questions, participants can unmute and ask. Okay, if there are no questions, we'll wind up the session.
Yeah.
So I extend my heartfelt thanks to our speaker, Mr. Ben Samuel, for delivering such an insightful and enriching session. Your expertise and clarity have greatly added value to today's program. So thank you, sir, for sharing your time, knowledge, and experience with us. We truly appreciate your contribution. Thank you, sir.
Thank you, ma'am. Thank you. Thank you for the opportunity. Thank you for the organizers for giving me the time and opportunity.
Thank you, sir. Yeah. So, dear participants, we'll have a short break and we look forward to giving you the same strength by attending the next session at 2 p.m. So, I kindly request all the participants to join the meeting 10 minutes before the session starts. So, thank you all.